Picture this. It's 1967. A massive 28-ton aircraft approaches the USS Coral Sea at 150 miles per hour. The pilot can barely see the deck through his narrow cockpit windows. The aircraft carrier's deck crew holds their breath as this flying behemoth, longer than a city bus and heavier than 3 elephants, attempts to land on a moving postage stamp in the middle of the ocean. The arresting cables strain under the enormous weight. The deck literally flexes and groans. This isn't just any landing attempt. This is the F-111B Sea Vark, and it's about to become one of aviation history's most spectacular failures. Welcome to Never Built, where we explore the magnificent disasters that shaped our world. I'm your host, and today we're diving deep into one of the Cold War's most ambitious technological gambles, a project so audacious, so fundamentally flawed, that it nearly broke the United States Navy's carrier aviation program. Before we begin this incredible journey through engineering hubris and military miscalculation, make sure to subscribe to our channel and hit that notification bell. We're constantly uncovering new stories of humanity's greatest what-ifs, and trust me, you don't want to miss what's coming next. And after you've heard this tale of the Sea Vark's spectacular demise, drop a comment below and tell us, what do you think was the biggest mistake in this project? Was it pure ambition or a fundamental misunderstanding of naval aviation? Let me know your thoughts. The F-111B Sea Vark represents everything that could go wrong when brilliant minds, unlimited budgets, and Cold War paranoia collide. This is the story of how the United States military tried to force a square peg into a round hole, literally attempting to squeeze a massive land-based bomber onto the cramped deck of an aircraft carrier. It's a tale of revolutionary technology, bureaucratic stubbornness, and the kind of engineering challenges that would make even today's aerospace engineers break out in a cold sweat. Over the next 7 chapters, we'll explore how this technological marvel became a cautionary tale, how its failures led to one of the most successful fighter jets in history, and why sometimes the most important innovations come from learning what doesn't work. So settle in, because we're about to witness one of the most expensive lessons in aviation history. The year was 1961, and America was scared. Not the kind of everyday fear you might feel walking alone at night, but the bone-deep existential terror that comes from knowing your enemy has weapons that could end civilization as we know it. The Soviet Union had just unveiled the Tupolev Tu-22 Blinder, a supersonic bomber capable of carrying nuclear weapons at speeds that made existing American interceptors look like they were standing still. Secretary of Defense Robert McNamara sat in his Pentagon office, staring at intelligence reports that painted a terrifying picture. Soviet bombers and cruise missiles were getting faster, flying higher, and carrying bigger payloads. Meanwhile, American aircraft carriers, the backbone of naval power projection, were essentially sitting ducks. Their existing fighter aircraft could barely reach 200 miles from the fleet before running low on fuel, creating a massive vulnerability gap that Soviet strategists were undoubtedly planning to exploit. The Navy's problem was simple to understand, but seemingly impossible to solve. They needed an aircraft that could fly far enough to intercept Soviet threats before they got anywhere near the carrier battle group, carry enough fuel to loiter for hours on patrol, pack sufficient firepower to destroy multiple targets, and somehow still be small and light enough to operate from an aircraft carrier deck. Oh, and it needed to do all of this while incorporating the latest in radar technology and missile systems. Enter the Tactical Fighter Experimental Program, better known as TFX. McNamara, a former Ford Motor Company executive who believed in the efficiency of shared platforms, had a revolutionary idea. Why not create one aircraft that could serve both the Air Force and Navy? The Air Force needed a low-level penetration bomber that could slip under Soviet radar and deliver nuclear weapons. The Navy needed a long-range interceptor. Surely, McNamara reasoned, smart engineers could design one airframe that could do both jobs. It was the kind of thinking that looked brilliant on paper and in boardroom presentations. One aircraft program instead of two meant shared development costs, common spare parts, streamlined training, and massive economies of scale. The Pentagon's accountants practically salivated at the projected savings. But, as any engineer will tell you, compromise is the enemy of excellence, and trying to make one machine do two completely different jobs often results in a machine that does neither job particularly well. The specifications that emerged from this planning process were nothing short of extraordinary. The aircraft needed to carry the massive AWG-9 radar system, a technological marvel that could track multiple targets simultaneously at ranges exceeding 100 miles. It needed to accommodate the equally impressive AIM-54 Phoenix missile, a weapon so advanced and expensive that each one cost more than a luxury car. The plane needed variable sweep wings to provide both high-speed performance and acceptable landing characteristics. And somehow, all of this technology needed to fit into an airframe that could operate from the constrained environment of an aircraft carrier. General Dynamics, the company that won the contract, faced an engineering challenge that bordered on the impossible. They were essentially being asked to take their F-111 Vark, a large, heavy, land-based aircraft designed for completely different missions, and somehow make it work on a carrier deck. It was like being asked to convert a freight train into a sports car while maintaining the freight capacity. The F-111A Aardvark was already pushing the boundaries of what was possible in aviation technology. Its variable sweep wing system was revolutionary, but complex and heavy. Its terrain-following radar was cutting-edge, but required substantial computing power and space. Its twin engines provided impressive performance, but consumed fuel at prodigious rates. Now, the Navy variant would need to incorporate even more systems while somehow becoming lighter and more maneuverable. What do you think? Was McNamara's vision of a common fighter platform fundamentally flawed from the start? Or could better execution have made it work? The comments section is waiting for your thoughts on this fascinating intersection of politics, technology, and military strategy. The engineers at General Dynamics knew they were attempting something that had never been done before. They were trying to create an aircraft that could perform air-to-air combat missions requiring agility and speed, while also serving as a long-range patrol aircraft requiring endurance and payload capacity. These requirements pulled the design in opposite directions, creating compromises that would ultimately doom the project. But in 1961, with Cold War tensions at their peak and the promise of revolutionary technology on the horizon, anything seemed possible. The F-111B Sea Vark was about to begin its journey from ambitious dream to expensive nightmare, and the lessons learned from its failure would reshape naval aviation for decades to come. By 1963, the first F-111B prototypes were taking shape in General Dynamics' Fort Worth facility, and the engineering team was beginning to realize the magnitude of their challenge. What had seemed achievable on paper was proving to be a nightmare in metal and composites. The aircraft that emerged from the factory floor was a beast, beautiful in its technological sophistication, but utterly unsuited for the environment it was designed to operate in. The numbers tell the story better than words ever could. The F-111B weighed 58,000 pounds when fully loaded. That's 29 tons of aircraft trying to land on a moving deck. To put this in perspective, the Navy's existing F-4 Phantom, already considered a heavy aircraft, weighed only 38,000 pounds. The Sea Vark was carrying an additional 10 tons of weight, equivalent to adding 2 full-sized automobiles to an already massive aircraft. This weight wasn't just a number on a specification sheet. It was a fundamental problem that affected every aspect of carrier operations. Aircraft carriers use steam catapults to launch planes, and these catapults have limits. The arresting gear that catches landing aircraft also has limits. The deck itself has structural limits. The F-111B was pushing all of these systems beyond their design parameters, and the results were predictably problematic. But weight was just the beginning of the Sea Vark's problems. The aircraft's dimensions were equally challenging. At 63 feet in length with its wings swept forward, the F-111B was longer than many of the Navy's existing aircraft. More problematically, its wingspan varied from 32 feet when swept back to 70 feet when extended. This variable geometry, while aerodynamically brilliant, created massive headaches for carrier deck operations where space is measured in inches, not feet. The cockpit design presented another set of challenges that would prove nearly insurmountable. The F-111B used a side-by-side seating arrangement, with the pilot and radar intercept officer sitting next to each other rather than in the traditional tandem configuration used by most fighters. This arrangement was chosen to facilitate crew coordination during long patrol missions, but it created a cockpit that was wide rather than narrow, further complicating the aircraft's integration with carrier systems. More critically, the side-by-side seating arrangement, combined with the aircraft's long nose and the positioning of various antennas and sensors, created severe visibility problems during carrier approaches. Pilots reported that they could barely see the carrier deck during the critical final moments of landing. In carrier aviation, where pilots need to maintain visual contact with the landing signal officer and judge their approach angle with split-second precision, this visibility problem was potentially fatal. The AWG-9 radar system, while technologically impressive, added its own complications. This radar was enormous. The antenna alone weighed several hundred pounds and required a nose cone large enough to house it properly. The system's power requirements were substantial, demanding generators and cooling systems that added even more weight and complexity to an already overburdened aircraft. The Phoenix missile system created additional challenges. Each AIM-54 Phoenix missile weighed nearly 1,000 pounds and measured 13 feet in length. The F-111B was designed to carry 6 of these missiles simultaneously, adding 6,000 pounds of ordnance to an aircraft that was already struggling with weight issues. The missile's size also required special accommodation in the aircraft's weapon bays, further complicating the internal layout and adding structural weight. General Dynamics engineers found themselves caught in an impossible situation. Every attempt to solve one problem seemed to create 2 new ones. Reducing weight meant sacrificing capability. Improving visibility meant redesigning major structural elements. Accommodating the required systems meant accepting compromises in performance and handling characteristics. The variable sweep wing system, while innovative, proved to be a maintenance nightmare. The mechanism required hundreds of moving parts, multiple hydraulic systems, and complex control algorithms. Each wing sweep position required different flight characteristics and handling procedures, multiplying the training requirements for pilots and maintenance crews. The system was also prone to failures that could leave an aircraft with asymmetric wing positions, a potentially catastrophic situation during carrier operations. Testing revealed additional problems that hadn't been anticipated during the design phase. The F-111B's approach speed was significantly higher than existing carrier aircraft, requiring longer deck runs and putting additional stress on arresting gear. The aircraft's sink rate during landing approaches was also problematic, creating hard landings that stressed both the airframe and the carrier deck structure. Perhaps most troubling of all, early flight tests revealed that the F-111B's performance fell short of specifications in almost every category. The aircraft was slower than promised, had less range than required, and handled poorly in air-to-air combat scenarios. The additional weight and complexity had degraded performance to the point where the aircraft could barely meet its basic mission requirements. What's your take on this engineering challenge? Do you think the problems were inevitable given the ambitious requirements, or could different design choices have saved the program? Share your thoughts in the comments. I'm particularly interested in hearing from anyone with engineering or aviation experience. By 1964, it was becoming clear that the F-111B Sea Vark was not just facing technical challenges. It was confronting fundamental laws of physics and engineering that couldn't be overcome through clever design or advanced materials. The aircraft was simply too big, too heavy, and too complex for successful carrier operations. But the program had already consumed hundreds of millions of dollars, and the Cold War pressure to field an effective fleet defense system remained as intense as ever. December 18, 1965. Test pilot Ralph Donnell climbed into the cockpit of the first F-111B prototype at Grumman's Calverton facility on Long Island. The aircraft, sitting on the tarmac, looked impressive. Sleek lines, sophisticated systems, the promise of revolutionary capability. But, as Donnell would later recall, the moment he attempted to taxi the aircraft, he knew they were in trouble. The F-111B didn't just feel heavy, it felt wrong. The controls were sluggish, the aircraft's response to pilot inputs was delayed, and the visibility from the cockpit was even worse than the engineers had predicted. During that first flight, Donnell reported that the aircraft handled like a pregnant whale, and that landing it on a carrier deck would require a miracle and a very long runway. The initial flight test program revealed problems that went far beyond what anyone had anticipated. The F-111B's thrust-to-weight ratio was abysmal, barely adequate for takeoff from a long runway, completely insufficient for the short, rolling deck of an aircraft carrier. The twin Pratt & Whitney TF-30 engines, while powerful on paper, couldn't overcome the aircraft's massive weight and aerodynamic compromises. Carrier qualification trials began in 1966 aboard the USS Coral Sea, and they were nothing short of disastrous. The first attempted landing nearly ended in catastrophe when the aircraft's approach speed proved too high for the ship's arresting gear. The cables stretched beyond their design limits, and the deck crew reported feeling the entire ship shudder under the impact. One crew member later described it as like watching a freight train try to land on a surfboard. The problems weren't just mechanical, they were fundamental. The F-111B's landing approach required such a steep angle that pilots lost sight of the carrier deck during the critical final seconds of approach. The aircraft's long nose and wide cockpit created blind spots that made precision landing nearly impossible. Pilots reported having to guess where the deck was during the final moments of touchdown, a situation that was clearly unacceptable for routine carrier operations. Even when landings were successful, the aircraft's weight created new problems. The arresting cables, designed for much lighter aircraft, were stretched beyond their elastic limits. The deck structure itself began showing signs of stress, with reports of cracked plates and bent support beams. The catapult systems required modifications to handle the additional weight, and even then, launches were marginal at best. The maintenance requirements were equally problematic. The F-111B's complex systems required specialized tools, extensive training, and maintenance procedures that were completely incompatible with shipboard operations. The variable sweep wing mechanism alone required more maintenance hours than entire conventional aircraft. In the space-constrained environment of an aircraft carrier, where every square foot is precious, the F-111B's maintenance footprint was simply unacceptable. Pilots began referring to the aircraft as the flying brick or the lead sled, nicknames that reflected their frustration with its poor performance characteristics. The aircraft's acceleration was sluggish, its climb rate was inadequate, and its maneuverability in air-to-air combat scenarios was described by one test pilot as suitable for formation flying with cargo planes, but not much else. The AWG-9 radar system, while technologically advanced, proved to be unreliable in the harsh environment of carrier operations. Salt air corroded sensitive components, vibration from catapult launches disrupted delicate electronics, and the system's power requirements strained the aircraft's electrical systems. During one test flight, the radar system failed completely, leaving the crew flying blind in a scenario that would have been tactically disastrous in combat. The Phoenix missile system added its own complications to flight operations. The missile's weight and size affected the aircraft's center of gravity, requiring careful load planning for each mission. The weapon bay doors, designed to accommodate the large missiles, were prone to jamming, and the missile launch sequence was so complex that it required extensive crew coordination and perfect timing. Perhaps most damaging to the program's credibility were the performance comparisons with existing aircraft. The F-4 Phantom, despite being older and less technologically advanced, consistently outperformed the F-111B in air-to-air combat exercises. The Phantom was faster, more maneuverable, easier to maintain, and far better suited to carrier operations. Military observers began questioning why the Navy was spending billions of dollars to develop an aircraft that performed worse than systems already in service. The cost overruns were becoming astronomical. Each F-111B prototype was costing nearly 10 times the price of a conventional fighter aircraft, and the program was consuming resources that could have been used to purchase hundreds of proven aircraft. Congressional oversight committees began asking pointed questions about the program's viability and the wisdom of continuing development. By 1967, it was clear that the F-111B was not just experiencing growing pains. It was fundamentally unsuited for its intended mission. The aircraft that was supposed to revolutionize fleet air defense was instead becoming a cautionary tale about the dangers of technological overreach and bureaucratic stubbornness. What's your opinion on this situation? Should the Navy have recognized the fundamental problems earlier and canceled the program? Or was persistence in the face of technical challenges the right approach? The engineering lessons from this period continue to influence aircraft design today, and I'd love to hear your thoughts on what could have been done differently. Despite mounting evidence of the program's problems, political and institutional pressures kept the F-111B alive. Too much money had been invested, too many careers were tied to its success, and the Cold War need for fleet defense remained urgent. The program would continue for several more years, consuming additional billions of dollars while producing an aircraft that would never see operational service. But from this expensive failure would emerge valuable lessons, and eventually one of the most successful fighter aircraft in naval aviation history. Captain James Morrison stood on the bridge of the USS Coral Sea in the spring of 1968, watching what he would later describe as the most terrifying display of aviation incompetence he had ever witnessed. Below him on the flight deck, another F-111B Sea Vark was preparing for launch, and Morrison knew from bitter experience that this attempt would likely end in disaster, embarrassment, or both. The Coral Sea had been chosen as the primary test platform for F-111B carrier trials, and the ship's crew had quickly learned to dread these operations. The aircraft was simply too large, too heavy, and too unwieldy for safe carrier operations. Every launch was a white-knuckle experience. Every landing was a potential catastrophe, and the ship's systems were being pushed far beyond their design limits. The problems began before the aircraft even moved. The F-111B's wingspan, even when swept back, required special handling procedures that disrupted normal flight deck operations. The aircraft couldn't be positioned in standard parking spots, couldn't be moved through normal traffic patterns, and required so much deck space that other operations had to be suspended whenever a Sea Vark was being prepared for flight. The catapult launches were particularly problematic. The F-111B's weight required maximum catapult power, but even then, the aircraft barely achieved flying speed by the end of the deck. Pilots reported that the aircraft would literally fall off the end of the carrier before gaining enough airspeed to climb. Several test flights ended with the aircraft skimming just above the ocean surface for miles before finally gaining altitude, a situation that would have been fatal in combat conditions with a full weapons load. The steam catapult systems themselves were being damaged by the repeated stress of launching such heavy aircraft. Maintenance crews reported cracked pistons, stretched cables, and worn components that required constant replacement. The catapults, designed to launch aircraft weighing 30,000 to 40,000 pounds, were being asked to handle loads 50% heavier than their design specifications. Landing operations were even more dangerous. The F-111B's approach speed was so high that pilots had only seconds to make corrections during the final approach. The aircraft's poor visibility meant that pilots often couldn't see the landing signal officer's corrections until it was too late to respond. Several test flights ended with the aircraft missing the arresting wires entirely and requiring emergency go-arounds, a procedure that was extremely dangerous given the aircraft's marginal performance characteristics. When the F-111B did successfully engage the arresting wires, the results were often spectacular in the worst possible way. The aircraft's weight would stretch the cables far beyond their normal limits, creating a violent deceleration that stressed both the aircraft and the ship's structure. Deck crews reported that they could feel the entire carrier flex under the impact, and several arresting wire assemblies were damaged beyond repair during the test program. The ship's elevators presented another set of challenges. The F-111B was so large that it barely fit on the deck elevators, and its weight was close to the maximum lifting capacity. Moving the aircraft between the flight deck and hangar deck became a complex operation requiring special procedures and extensive safety precautions. On several occasions, elevator mechanisms were damaged by the aircraft's weight, requiring expensive repairs and operational delays. In the hangar deck, the F-111B's size created a logistics nightmare. The aircraft was so large that it blocked access to other aircraft and maintenance areas. Its complex systems required specialized support equipment that took up additional space, and its maintenance requirements were so extensive that entire sections of the hangar had to be dedicated to Sea Vark operations. The maintenance challenges were particularly severe in the corrosive environment of shipboard operations. The F-111B's sophisticated electronics were not designed for the salt air, high humidity, and constant vibration of carrier operations. Systems that worked perfectly in land-based test facilities failed repeatedly at sea, requiring constant repairs and component replacements that were difficult to perform in the confined spaces of a ship. The variable sweep wing mechanism was especially problematic in the maritime environment. Salt corrosion affected the hydraulic systems, and the complex mechanical components required constant lubrication and adjustment. Several test flights were canceled when the wing sweep mechanism failed during pre-flight checks, and on one memorable occasion, an aircraft returned to the carrier with its wings locked in an asymmetric position, a situation that made landing extremely dangerous. The fuel consumption rates were another major problem for carrier operations. The F-111B burned fuel at such a prodigious rate that it significantly reduced the carrier's operational range and endurance. The ship's fuel storage and transfer systems were strained by the aircraft's requirements, and flight operations had to be carefully planned around fuel availability. Perhaps most troubling from an operational standpoint was the F-111B's impact on overall carrier effectiveness. The aircraft required so many special procedures, consumed so many resources, and created so many operational restrictions that the entire air wing's capability was degraded. Other aircraft couldn't operate normally when Sea Varks were on deck, maintenance schedules were disrupted, and the carrier's ability to conduct sustained operations was severely compromised. The psychological impact on the crew was equally significant. Sailors and officers who had spent their careers working with reliable, proven aircraft systems found themselves dealing with a machine that seemed to break down constantly, required extraordinary precautions, and posed genuine safety risks to ship and crew. Morale suffered, and confidence in the program plummeted. By late 1968, it was clear that the F-111B was not just unsuitable for carrier operations, it was actively dangerous to the ships and crews attempting to operate it. The aircraft that was supposed to enhance fleet defense capability was instead degrading it, creating more problems than it solved, and consuming resources that could have been better used elsewhere. What do you think about the Navy's persistence in testing an aircraft that was clearly unsuitable for carrier operations? Was it scientific thoroughness or bureaucratic stubbornness? The lessons learned from these trials would eventually lead to much better aircraft, but at what cost in terms of resources, time, and safety? The Coral Sea's experiences with the F-111B would become legendary within naval aviation circles, not as an example of successful innovation, but as a cautionary tale about the importance of matching aircraft design to operational requirements. The ship and her crew had paid a high price to demonstrate that some engineering challenges simply cannot be overcome through determination and advanced technology alone. Lieutenant Commander Tom Connolly sat in a Pentagon briefing room in early 1968, staring at a stack of test reports that painted a devastating picture of the F-111B program. As the Navy's Deputy Chief of Naval Operations for Air Warfare, Connolly had been tasked with finding a way to salvage something useful from the Sea Vark disaster. What he discovered would ultimately lead to one of the most successful fighter programs in aviation history. But first, he had to convince his superiors to abandon a project that had already consumed over $3 billion. The numbers in Connolly's reports were damning. After 7 years of development and testing, the F-111B had failed to meet virtually every performance specification. It was too heavy, too slow, too unwieldy, and too unreliable for operational use. More critically, it had failed to demonstrate that it could actually perform the fleet defense mission it was designed for. In mock combat exercises, the Sea Vark consistently lost to older, simpler aircraft that cost a fraction of its price. But buried within the failure reports were some remarkable success stories. The AWG-9 radar system, despite its integration problems, represented a quantum leap in airborne radar capability. The system could track 24 targets simultaneously at ranges exceeding 100 miles, performance that was unmatched by any other airborne radar system in the world. The Phoenix missile system, when it worked properly, could engage targets at distances that made conventional air-to-air combat obsolete. Connolly realized that the Navy's fundamental mistake had been trying to build an aircraft around existing land-based technology rather than designing a purpose-built carrier aircraft that could accommodate the required systems. The F-111B's problems weren't with its mission systems, they were with the airframe that housed them. What if, Connolly wondered, they could take the good parts of the Sea Vark program and put them in an aircraft actually designed for carrier operations? The idea was revolutionary and risky. Convincing Congress and the Pentagon to fund another fighter program after the F-111B debacle would require extraordinary political skill and technical credibility. But Connolly had an ally in Admiral Thomas Moorer, the Chief of Naval Operations, who was equally frustrated with the Sea Vark's failures and equally convinced that the Navy needed a long-range fleet defense capability. In July 1968, Connolly presented his proposal to Secretary of the Navy Paul Nitze. Instead of trying to fix the unfixable F-111B, the Navy should cancel the program and start over with a clean sheet design. The new aircraft would be built specifically for carrier operations, incorporating lessons learned from the Sea Vark disaster while retaining its advanced radar and missile systems. The proposal was audacious in its scope and timing. The Vietnam War was consuming enormous resources, defense budgets were under intense scrutiny, and Congress was increasingly skeptical of expensive military programs that failed to deliver promised capabilities. Asking for funding to develop another fighter aircraft after the F-111B failure seemed like political suicide. But Connolly had done his homework. His presentation included detailed analysis showing that the AWG-9 radar and Phoenix missile systems were not just viable, they were revolutionary. These systems could provide fleet defense capabilities that were impossible with existing technology, but only if they were installed in an aircraft designed from the ground up to accommodate them. The technical specifications for the new aircraft were derived directly from the F-111B's failures. Where the Sea Vark was too heavy, the new aircraft would be lighter. Where the Sea Vark had poor visibility, the new aircraft would have excellent sightlines. Where the Sea Vark was underpowered, the new aircraft would have thrust-to-weight ratios suitable for carrier operations. Grumman Corporation, which had been the Navy's partner in the F-111B program, was eager to redeem itself after the Sea Vark disaster. The company's engineers had learned valuable lessons about carrier aircraft design during the troubled program, and they were confident they could build an aircraft that would succeed where the F-111B had failed. The new aircraft design that emerged from these discussions would eventually become the F-14 Tomcat. But in 1968, it was just a collection of drawings and specifications that promised to solve the problems that had doomed the Sea Vark. The Tomcat would be lighter, faster, more maneuverable, and specifically designed for carrier operations from the very beginning. The Phoenix missile system would be carried over virtually unchanged from the F-111B program. The missiles had proven their effectiveness during testing, and their long-range capability remained essential for fleet defense. The AWG-9 radar would also be retained, but it would be integrated into an airframe designed to accommodate its size and power requirements. The variable sweep wing concept would be retained as well, but with important modifications. The Tomcat's wing sweep mechanism would be simpler, more reliable, and better suited to the demanding environment of carrier operations. The wings themselves would be designed for the specific performance requirements of a carrier-based interceptor, rather than the compromised requirements of a multi-role aircraft. Perhaps most importantly, the new aircraft would be designed by engineers who understood carrier operations intimately. The F-111B had been designed by land-based aircraft specialists who had tried to adapt their design for carrier use. The Tomcat would be designed by carrier aircraft specialists from the very beginning, ensuring that every system and component would be optimized for shipboard operations. The political battle to secure funding for the new program was intense and prolonged. Critics argued that the Navy was simply trying to resurrect the failed F-111B under a different name. Supporters countered that the lessons learned from the Sea Vark disaster were invaluable and that the new aircraft would succeed precisely because it avoided the mistakes that had doomed its predecessor. In December 1968, Congress approved funding for what would become the F-14 Tomcat program. The decision was controversial and risky, but it was based on the recognition that the Navy's fleet defense requirements were real and urgent, and that the technology developed for the F-111B could be successfully adapted to a purpose-built carrier aircraft. What's your take on this decision? Was it wise to salvage the useful technology from a failed program? Or should the Navy have started completely fresh? The F-14 Tomcat went on to become one of the most successful fighter aircraft in history, but that success was built on the expensive lessons learned from the F-111B's failure. The transformation of the Sea Vark disaster into the Tomcat triumph would take several more years to complete, but the foundation was laid in those crucial months of 1968 when naval aviation leaders had the courage to admit failure and the wisdom to learn from it. The F-111B Sea Vark would never see operational service, but its legacy would live on in one of the most capable fighter aircraft ever built. On July 10, 1968, Secretary of Defense Clark Clifford stood before a packed congressional hearing room and uttered words that would echo through Pentagon corridors for decades. The F-111B program is hereby terminated. With that simple statement, one of the most expensive military aircraft programs in history came to an ignominious end, but the lessons it taught would reshape American military procurement for generations. The final cost of the F-111B program was staggering even by Cold War standards. Over $4 billion, equivalent to nearly $30 billion in today's money, had been spent to produce 7 test aircraft that would never see operational service. To put this in perspective, that money could have purchased over 800 F-4 Phantom fighters, enough to equip the entire Navy and Marine Corps with proven, effective aircraft. But the financial cost, enormous as it was, paled in comparison to the strategic cost. The United States Navy had spent 7 crucial years of the Cold War pursuing a technological dead end, while Soviet naval aviation capabilities continued to advance. The gap in fleet defense capability that the F-111B was supposed to close remained wide open, leaving American carrier battle groups vulnerable to exactly the kind of attacks the Sea Vark was designed to prevent. The program's failure had profound implications for American military procurement philosophy. The concept of commonality, building one aircraft to serve multiple services with different requirements, had been thoroughly discredited. The F-111B demonstrated that trying to make one machine do everything often results in a machine that does nothing particularly well. Robert McNamara, the Secretary of Defense who had championed the common aircraft concept, found his reputation permanently damaged by the Sea Vark disaster. His business school approach to military procurement, emphasizing cost savings and efficiency over mission-specific optimization, was largely abandoned in favor of service-specific programs that prioritized effectiveness over economy. The technical lessons learned from the F-111B failure were equally valuable, though expensive. The program had pushed the boundaries of several technologies simultaneously: variable sweep wings, advanced radar systems, long-range missiles, and complex avionics integration. While the overall aircraft was a failure, each of these individual technologies had been advanced significantly during the development process. The variable sweep wing technology, despite its problems in the F-111B, would go on to be successfully implemented in several other aircraft. The lessons learned about wing sweep mechanisms, control systems, and structural design would prove invaluable in later programs. The F-14 Tomcat, F-111 Vark, and Soviet aircraft like the MiG-23 all benefited from the expensive research conducted during the Sea Vark program. The AWG-9 radar system represented perhaps the program's greatest technological success. Despite integration problems with the F-111B airframe, the radar itself was a revolutionary achievement that would define air-to-air combat for the next 3 decades. The system's ability to track multiple targets simultaneously at long range gave American fighters a decisive advantage that would prove crucial in later conflicts. The Phoenix missile system, while problematic in the F-111B's cramped weapon bays, was fundamentally sound and would become one of the most feared air-to-air weapons in the world. The missile's range and accuracy were unmatched by any contemporary weapon, and its mere presence on American aircraft would serve as a powerful deterrent to potential adversaries. The program's management failures were as instructive as its technical problems. The F-111B had suffered from unclear requirements, inadequate oversight, and a fundamental disconnect between what the military needed and what the contractors delivered. These management lessons would lead to significant reforms in military procurement processes, including more rigorous testing requirements and better integration between military and contractor personnel. Perhaps most importantly, the F-111B failure demonstrated the critical importance of understanding operational requirements before beginning aircraft design. The program had started with a political decision to create a common aircraft and had then tried to force military requirements to fit that decision. Future programs would begin with clear operational requirements and then design aircraft to meet those specific needs. The human cost of the program was also significant, though harder to quantify. Dozens of test pilots, engineers, and military personnel had risked their lives testing an aircraft that was fundamentally unsuitable for its intended mission. Several near-fatal accidents during the test program highlighted the dangers of pushing flawed technology beyond its limits in pursuit of political and bureaucratic objectives. The international implications of the F-111B failure were equally serious. America's allies, who had been promised access to revolutionary fleet defense technology, were left with capability gaps that would take years to fill. The Soviet Union, meanwhile, gained valuable intelligence about American technological capabilities and limitations through careful observation of the program's public failures. The cancellation decision itself was controversial and painful. Thousands of jobs were lost when the program ended, and several congressional districts that had benefited from F-111B contracts faced economic hardship. The political fallout from the cancellation would influence defense procurement decisions for years, as politicians became more cautious about supporting expensive, high-risk military programs. But the cancellation also demonstrated institutional wisdom and courage. Military and political leaders had recognized that continuing a failed program would only compound the damage, and they had the courage to admit failure and change course. This willingness to acknowledge mistakes and learn from them would prove crucial in developing more successful programs in the future. The F-111B's failure also highlighted the importance of realistic testing and evaluation. The program had suffered from overly optimistic projections and inadequate testing that failed to reveal fundamental problems until enormous resources had already been committed. Future programs would implement more rigorous testing protocols and more realistic performance assessments. What do you think was the most important lesson from the F-111B failure? Was it the technical lesson about aircraft design, the management lesson about procurement processes, or the political lesson about the dangers of compromise in military requirements? The program's legacy continues to influence military aviation development today, and understanding its lessons remains crucial for anyone interested in aerospace engineering or military procurement. The F-111B Sea Vark had failed spectacularly, but its failure had taught invaluable lessons about the limits of technology, the importance of clear requirements, and the dangers of political interference in engineering decisions. These lessons would prove their worth in the years to come, as American military aviation entered a new era of more focused, more successful development programs. December 21st, 1970. Lieutenant Randy "Duke" Cunningham pushed the throttles forward on his brand-new F-14 Tomcat and felt the twin engines respond with a surge of power that the old F-111B could never have provided. As he lifted off from the deck of the USS Enterprise, Cunningham was experiencing the vindication of 7 years of expensive lessons learned from the Sea Vark disaster. The Tomcat was everything the F-111B should have been: fast, agile, powerful, and perfectly suited for carrier operations. The F-14 Tomcat's first flight represented more than just the debut of a new aircraft. It was the resurrection of American naval aviation's technological leadership after the humiliation of the F-111B failure. Every system in the Tomcat had been influenced by lessons learned from the Sea Vark program, and the result was an aircraft that would dominate the skies for the next 3 decades. The Tomcat retained the F-111B's most successful technologies while discarding everything that had made the Sea Vark unsuitable for carrier operations. The AWG-9 radar system was carried over virtually unchanged, giving the Tomcat the same revolutionary long-range detection capability that had been the F-111B's greatest strength. The Phoenix missile system was also retained, providing the Tomcat with unmatched long-range engagement capability. But everything else about the Tomcat was designed from scratch with carrier operations as the primary consideration. The aircraft was lighter, more maneuverable, and had excellent visibility from the cockpit. The variable sweep wing system was simplified and made more reliable. The engines provided adequate thrust-to-weight ratio for carrier operations. Most importantly, the entire aircraft was sized and configured for efficient carrier operations. The contrast between the two aircraft was stark and instructive. Where the F-111B weighed 58,000 pounds, the Tomcat weighed 43,000 pounds, a weight reduction of 15,000 pounds that made all the difference in carrier operations. Where the F-111B had poor visibility and sluggish controls, the Tomcat had excellent sightlines and responsive handling. Where the F-111B had been a maintenance nightmare, the Tomcat was designed for shipboard maintenance from the beginning. The F-14's success vindicated the decision to cancel the F-111B and start over with a clean-sheet design. The Tomcat would go on to serve with distinction for over 30 years, participating in conflicts from the Cold War through the Iraq War. Its combination of speed, range, and firepower made it one of the most feared fighter aircraft in the world, and its presence on American aircraft carriers served as a powerful deterrent to potential adversaries. The Phoenix missile system, which had been problematic in the F-111B's cramped weapon bays, found its perfect home in the Tomcat's spacious fuselage. The missile's legendary range and accuracy would be demonstrated in combat during the Iran-Iraq War, where Iranian F-14s used Phoenix missiles to achieve kills at ranges exceeding 60 miles, distances that made traditional air-to-air combat tactics obsolete. The AWG-9 radar system also reached its full potential in the Tomcat. The radar's ability to track multiple targets simultaneously at long range gave Tomcat crews unprecedented situational awareness and engagement capability. During the Cold War, Soviet pilots learned to fear the distinctive radar signature of the AWG-9, knowing that detection by a Tomcat often meant they were already within range of a Phoenix missile. But the F-111B's legacy extended far beyond the technologies it contributed to the Tomcat. The program's failure had taught fundamental lessons about military procurement that would influence American defense programs for decades. The concept of service-specific aircraft designed for particular missions became the standard approach, replacing the failed commonality concept that had doomed the Sea Vark. The program also demonstrated the importance of realistic testing and honest evaluation. The F-111B had suffered from overly optimistic projections and inadequate testing that failed to reveal fundamental problems until enormous resources had been committed. Future programs would implement more rigorous testing protocols and more realistic performance assessments, saving billions of dollars and years of development time. The management lessons learned from the F-111B failure were equally valuable. The program had suffered from unclear requirements, inadequate oversight, and poor communication between military users and contractor developers. These problems led to significant reforms in military procurement processes, including better integration between military and contractor personnel and more rigorous oversight of major programs. The F-111B's influence can also be seen in the development of other successful aircraft programs. The F-16 Fighting Falcon, F-18 Hornet, and later stealth aircraft all benefited from lessons learned during the Sea Vark disaster. These programs emphasized clear requirements, realistic testing, and close cooperation between military users and aircraft manufacturers. The variable sweep wing technology pioneered in the F-111B would find successful application in several other aircraft. The F-111 Aardvark, despite sharing the F-111B's designation, was actually a successful land-based aircraft that served effectively for decades. Soviet aircraft, like the MiG-23 and Tu-22 backfire, also used variable sweep wings based partly on technology observed during the F-111B program. The international implications of the F-111B failure and Tomcat success were significant. America's allies, who had been disappointed by the Sea Vark's cancellation, were impressed by the Tomcat's capabilities, and several nations sought to purchase the aircraft. The Tomcat's success helped restore confidence in American military technology after the embarrassment of the F-111B failure. The Soviet Union, meanwhile, was forced to develop countermeasures to the Tomcat's capabilities. The combination of the AWG-9 radar and Phoenix missile system represented a quantum leap in air-to-air combat capability that Soviet aircraft could not match. This technological gap would influence Soviet aircraft development for the remainder of the Cold War. The F-111B program also highlighted the importance of understanding the operational environment before beginning aircraft design. The program had failed because its designers had not fully appreciated the unique challenges of carrier operations. Future naval aircraft programs would begin with extensive study of carrier operations and would involve carrier-experienced personnel from the earliest design phases. The economic lessons from the F-111B failure were equally important. The program demonstrated that trying to save money through commonality could actually be more expensive than developing separate optimized aircraft for different missions. This lesson would influence procurement decisions for decades as military planners learned to value effectiveness over theoretical cost savings. Today, more than 50 years after the F-111B's cancellation, its lessons continue to influence military aircraft development. Modern programs like the F-35 Lightning II have attempted to achieve some degree of commonality between different variants, but they have done so with much greater attention to the specific requirements of each service and operating environment. The F-111B Sea Vark represents one of aviation history's most expensive lessons, but it was also one of the most valuable. The program's failure taught fundamental truths about aircraft design, military procurement, and the importance of matching technology to operational requirements. These lessons helped create the foundation for decades of successful American military aviation programs. What do you think is the most important legacy of the F-111B program? Was it the technological innovations that led to the Tomcat's success, the management lessons that reformed military procurement, or the strategic insights about the importance of service-specific aircraft design? The Sea Vark story continues to offer valuable lessons for anyone interested in engineering, military history, or the complex relationship between technology, and politics. The F-111B Sea Vark never achieved its intended mission of defending the fleet, but in failing, it taught lessons that would make American naval aviation stronger and more capable than ever before. Sometimes, the most important victories come from learning how to avoid defeat, and the Sea Vark's expensive failure paved the way for decades of success in the skies above the world's oceans. That's our journey through one of aviation history's most fascinating failures. The F-111B Sea Vark may have been a flying brick, but it was a brick that built the foundation for some of the most successful fighter aircraft ever created. If you enjoyed this deep dive into Cold War aviation history, make sure to subscribe for more stories of humanity's greatest technological ambitions and most instructive failures. And don't forget to share your thoughts in the comments. What other failed projects would you like to see us explore? Until next time, keep looking up and remember that sometimes our greatest failures teach us the most valuable lessons.